Okay, welcome back. Now, we're going to talk about L'Hopital's rule. So, L'Hopital's rule is something that is used when we have a quotient of functions. So, let's review what we learned before. Okay, so when we had a quotient of functions and we want to take the limit as x approached to a of f of x over g of x, right? And given that those functions were continuous and g was not equal to 0, we could write this as a quotient of limits, right? Using the limit laws. And so we would do the limit as x approached a of f of x over the limit as x approached a of g of x. Okay, now, the problem that we ran into in some cases, right, if there was the limit, right, would equal limit 1 over limit 2. But what if the limits were 0, right? So in some cases that you've seen, we would get this 0 over 0, which is what we call an indeterminate form, okay? Sometimes you'll see it with quotation marks because it does not mean we're dividing 0 by 0. It's really a representation of where the limits are going. And so it's indeterminate because it means we have to do a little bit more analysis to find the answer. Okay, for example, we've done limits like this. In fact, I've made mention of it. So here's one. The limit as x approaches 2 of x squared minus 4 over x minus 2. Okay? As x approaches 0, or excuse me, as x approaches 2, we get 0 over 0. But then, how do we solve this? How do we figure this out? Well, we had to investigate, right? So, okay, can we factor this? And so we said, okay, well, we can factor this and get rid of the discontinuity. Okay? So, as x approaches 2, we would factor the top as x minus 2 times x plus 2 over x minus 2. And then, of course, these cancel, right? And we get the limit as x approaches 2 of x plus 2, which equals 4. And then we finally got the answer. Okay, now, or there was another one. The limit as x approaches 0 of sine x over x, right? And so how do we solve that one? Well, that one we had to solve by using the squeeze theorem or looking at it graphically, right? And we found that the limit of this thing was equal to 1. Okay. Now, so those are ways that we can solve some equations, but we're going to introduce a way of using a different technique, which is L'Hopital's rule, for evaluating limits such as these, but not only these, but other limits that we would not have a chance that we wouldn't be able to calculate previously. Okay, so now the idea behind L'Hopital's rule is really based on linearizations, okay, or linear approximations. Okay, so let me start with this. Okay, so we can start with two continuous functions, f and g. So if f and g are continuous functions, okay, then we can approximate f and g. So f of x is approximately equal to f of x, or f of a, plus f prime of a times x minus a. Okay? And then similarly, we could say g of x is approximately g of a, oops, plus g prime of a. Okay? And so if we take the ratio of these things, right, since f and g are both continuous, we know, oh, the other thing too is let's assume that let's assume the limit, okay, we also want to assume the limit of the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x is equal to 0. Okay, so that's because that's the issue that we're dealing with, right, when we have an indeterminate form. So let's assume that these are continuous and their limits are both equal to 0. Okay. So now in order to investigate what the limit is, let's use these linear approximations. Okay, now, since they're continuous, we can take the ratio of these, right, and then we can consider what would happen. So let's consider f of x over g of x is going to be approximately equal to f of a plus f prime of a times x minus a, and g of a plus g prime of a times x minus a. Now, since f and g are continuous, okay, so here's what happens. Here's where it breaks down. Or excuse me, since f and g are differentiable, right, then they're continuous at a. So that means, based on this, that f of a equals the limit as x approaches a of f of x, which equals 0. Okay? And then similarly the same thing, since g is differentiable, g of a is equal to the limit as x approaches a of, oops, not f, g of x is also equal to 0. Okay? So that means, guess what? This equals, now this is 0 and this is 0, right? So now, what happens? If we take the limit, oops, so if we take the limit as x approaches a of f of x over g of x, then that's going to be approximately the limit as x approaches a of f of a plus f prime of a times x minus a divided by g of a plus oops, I can't want to write G or F. G prime of A times X minus A. Now, if I, since this is continuous, then also, if we, well, okay, since this is continuous, F and G are continuous, right? We can do these two, but also let's assume that F prime of G, or excuse me, F prime and G prime are also continuous. Then what happens is we can use the limit laws and we get the limit as X approaches A of F of A, right? Plus the limit, oh, hold on, no, I don't even need to do that. Hold on, let me go back. Since based on these, we know that these are both 0. So then what happens is this equals the limit as X approaches A of what? Well, these both are going to be 0. And this is going to be just F prime of A times X minus A, and G prime of A over X minus A, right? And then if we assume that F prime and G prime are continuous at X equals A, then we know F prime of A is equal to the limit as X approaches A of F prime of X. And same thing with G of X. So if these two are continuous, right? And so then we can conclude that, well, these are going to cancel, right? And we get the limit that we started with is going to be approximately equal to the limit of the ratio of the derivatives of the two functions. And so this is where what we call L'Hopital's rule. Okay. Now notice that a couple of things we assumed. We assumed that both F and G are continuous and that F prime and G prime are also, or excuse me, I'm sorry, differentiable. I keep saying continuous. That F and G are differentiable, but we're also saying that F prime and G prime are differentiable, which implies that they're also continuous. Okay? That's what I wanted to say. And so that's the idea of L'Hopital's rule. So anytime we have differentiable functions, or ratio of differentiable functions where we get 0 over 0 as an indeterminate form, we can apply L'Hopital's rule. As long as the functions are differentiable and their derivatives are differentiable, we can apply it. And that's it. Next, we'll introduce the theorem, which we're going to call L'Hopital's rule. Have a good day.